In this lecture, we will look at some more applications of Bernoulli's equation, and then subsequently we will have a brief look at potential flow and boundary layer flow. So, last time we had looked at flow through a converging diverging duct, where we continued to assume that the flow was inviscid, incompressible and devoid of any body forces. So, that is how we could first work out how the continuity equation looks across the inlet and the outlet of that duct. Basically, we can apply this law to any station along the length of the duct, and additionally we looked at how along the length of the duct the pressure would vary and how we can work it out by combining the continuity equation with Bernoulli's equation. Now, if you look at a practical application of this converging diverging duct, in wind tunnels, we make elaborate use of ducts having changing cross sectional area as you move along the wind tunnel facility. So, this is typically a cross sectional view of a low speed wind tunnel with appropriate supports to mount it on the floor of a laboratory, and it is driven by a fan at one end of the tunnel, which is powered by an electrical motor, and the motor is basically shrouded so that you could reduce the aerodynamic drag, and then when this fan runs, it creates a suction whereby flow is brought into the tunnel through its inlet section, which is often in the form of a bell mouth structure, and then it has a large cross sectional area chamber, which is called as the settling chamber, followed by a reducing cross section, which is often called as nozzle or converging section, and then it is brought into the test section, which basically has the lowest cross section, and this is where we mount the models for testing, where the highest velocities are available. Additionally, by the time the flow reaches this test section, it is also free from disturbances as far as possible, based on how well the flow has been treated inside the settling chamber. There are a lot of fine meshes which are put inside the settling chamber, which makes the flow very quiet. And then further, as it moves down from the test section, it moves into the diffuser, where the cross sectional area again increases, but it increases gradually. That is to keep the adverse pressure gradient under control, so that the flow does not separate off. Remember that the wind tunnel is going to handle a real flow which has viscous stresses in it. So, while it handles the viscous flow, it is very much prone to flow separation due to adverse pressure gradient, and thereby you have to keep a long diffuser where you gradually increase the pressure of the flow and make sure that there is no flow separation. And then finally, the flow moves through the fan and leaves the test section, leaves the wind tunnel. So, this is an open circuit low speed wind tunnel, where the continuity equation as we have derived it will work very well, but you have to carefully apply the Bernoulli's equation across different sections, because you have to be careful about the assumption of inviscid. How far will it be valid? You can say that if there is a very thin layer adjacent to the wall, where the viscous effects are by and large confined, which we call as the boundary layer, and the remaining flow is by and large inviscid, and we are choosing points in the flow field which are basically located in the inviscid region, then this equation will work fairly well. So, in practical applications, we have to be careful in how we apply the Bernoulli's equation. So, we will look at one or two more applications gradually. So, let us say we are taking 2 points on the surface of the wind tunnel. Let us say the 2 points are located here, and we are calling these 2 points as 1 and 2. And if you look very closely at those 2 points, there will be 2 slots which are made on the wall, and some tubing is provided from that slot all the way up to a manometer, where it is connected to one limb of the manometer, and a similar small port is made at that point 2, from where again another limb comes and joins, another tube comes and joins the other limb of the manometer. And then you may find that the manometric liquid is occupying levels like this in the 2 limbs, and there is a difference in height between the 2 levels. So, if we assume the manometric fluid has a density of rho f, f for the fluid, then if we apply the principle that at the same elevation or height, if we choose 2 points A and B, then the pressures at those 2 points are equal, and based on that principle, we could write that P 1 is equal to P 2 plus delta H rho f g. So, P 1 is sensed by this side, P 2 by this side of the manometer. P 1 is larger than P 2, and therefore, the manometric liquid is pushed further down on the limb which is connected to the P 1 side, and the difference in pressure between the two is basically given by the hydrostatic pressure equation. H times rho times g. So, from here one can say that if you have knowledge about the velocity at any one particular section, let us say you know what the velocity is at section 1, then you can work out what the velocity at section 2 will be, or the point 2 will be. So, that will come out to be delta H rho f g plus half rho v 1 square into 2 by rho. Try deriving this equation at home by making use of Bernoulli's equations between the points 1 and 2. So, we saw one more application of Bernoulli's equation here, And further, let us look at a very important experimental device which we call as the pitot-static tube. So, here a cross sectional view is shown, and it is shown in a highly zoomed manner. Typical dimensions of this pitot tube may be only a few millimeters. Let us mark a few important points in and around the pitot tube. So, we are looking at this experimental device which is called as pitot-static tube. Of course, it has a tubular structure, but it has different orifices. So, it has one orifice which senses stagnation pressure. And there is another orifice which senses static pressure. Let us say it is immersed in a flow field and we are drawing some typical streamlines. In order to sense the pressures at these two orifices, again of course, we have to make connections, we have to have tubings, so that we can reach that pressure signal to an appropriate device. In this case, we are using a manometer. You might as well use other devices, which we will discuss at more length later on in the course. So, it is finally routed to a manometer, and you will find that one of the pressures will be distinctly higher than the other. The higher pressure happens to be the stagnation pressure, which is measured by the orifice which is at the tip of the pitot-static tube, and thereby the manometric fluid will be lower on that limb of the manometer. Again, of course, you can do the delta H based calculations in order to link the two pressures. Now, let us look at the concept of these the two pressures which we are sensing at the 2 points. So, if you follow the streamline A B, then the flow velocity what you have at the point A, if you call it as V A, that gradually decreases as you move towards the point B, and then typically by the time it reaches point B, it goes to 0. That means, it slows down and comes to a halt. When this pitot-static tube is just introduced into the flow field, some air manages to get into this spacing and move all the way and fill up this space. Once that is over, then no more air can further enter that passage, and therefore, it has to come to a halt by the time it reaches B. Therefore, if you follow this streamline, the velocity has to continuously decrease to 0. This is called as the stagnation streamline. If you follow another streamline and you look at 2 points along that streamline, let us say C and D, then what you find is that at both the points the velocities are non-zero, and at the point D what you are sensing is basically the pressure of the air which is moving past that orifice. So, in a dynamic condition, in flowing air you are trying to sense the pressure. So, as a fluid element crosses that point D, it just impresses a pressure upon that orifice, which is basically sensed by the other limb of the manometer. So, that is what is called as the static pressure. Now, the stagnation pressure is indicated by the nomenclature P naught, and in this flow field we continue to make the assumptions for Bernoulli's equation, and we write down the expression for stagnation pressure, that is the sum of static pressure and dynamic pressure. Remember that this definition of the dynamic pressure holds good for any kind of air speeds that you are talking about, from very low speeds, typically incompressible flows, to very high supersonic flows also. The definition of dynamic pressure will remain as it is, but the relation that the difference between stagnation pressure and static pressure is going to be equal to the dynamic pressure, this holds good only for inviscid incompressible flow that you are handling. It does not hold good for compressible flows. Even if you assume it to be inviscid, it will not work for compressible flows. This is a very, very important point that one has to keep in mind. So, we learned about a very important instrument through which you can make measurements of stagnation pressure and static pressure, and if you feed them to the two limbs of a manometer, you get the difference, and from there you can sense the dynamic pressure, and basically that should give you an assessment of the flow velocity where the probe is inserted, because the difference happens to be half rho v square, from which you can certainly extract the information about the velocity. Earlier we had discussed about several non-dimensional coefficients, of which pressure coefficient was an important one. We are revisiting the pressure coefficient once again over here. You may recall that the nomenclature was Cp, and we are going to define it as P minus P infinity into half rho infinity u infinity square. This is basically dynamic pressure of the free stream. Dynamic pressure is often represented by the letter Q. So, what is it talking about? It is talking about a pressure at some point in the flow field, and we are trying to make a non-dimensional assessment of that pressure. So, if you were looking at a situation like this, that there is an uniform flow moving past an airfoil, and you are interested to find out the pressure coefficient at a point on the airfoil, then if we apply Bernoulli's equation between a point in the free stream and the point P on the airfoil, then we see that Cp will turn out to be let us use half rho infinity everywhere, that will make it consistent. And then you will find that it reduces to this. So, this is an expression which is again valid only for incompressible flows, and remember that at stagnation point, for example, u will be equal to 0, and therefore, Cp will be equal to 1. So, in incompressible flows, the Cp equal to 1 is the maximum which occurs at the stagnation point. Now, in compressible flows, on the other hand, Cp exceeds 1 at a stagnation point. When we learn about stagnation flows in compressible flows, we will see why. And then again from this expression you can figure out that there may be locations where u is becoming greater than u infinity. Locally the flow is accelerating. You saw earlier in the airfoil problem that the free stream velocity was of the order of 45 meters per second, while the local velocity on the airfoil was about 136 meters per second. So, that was way above the u infinity. So, in that situation what happens? Cp becomes negative. So, the moment the pressure falls below the free stream static pressure, the Cp becomes negative. So, these are some very important lessons that we have learned by applying Bernoulli's equation. Now, let us look at the governing equation for irrotational incompressible flow, by means of which we will be able to obtain information about the velocity field from this equation, and this equation is called as Laplace equation. Now, we know that the moment we make the incompressible assumption, it automatically means that if we are taking the material derivative or substantial derivative of the volume of a fluid element, that will be equal to 0. And as a consequence, what happens is that from the continuity equation, you can on one hand show that the governing equation for incompressible flows will be divergence V equal to 0. On the other hand, from this definition itself, we can argue that a divergence of velocity can be equal to 0. That is because when it comes to divergence of velocity, it is by definition the time rate of change of volume of a moving fluid element per unit volume. And since volume of the fluid element is not changing, because any pressure changes are not accompanied by density changes, therefore, we have the condition of divergence V equal to 0 in this case. And from the continuity equation point of view, how we can show this is that if we invoke the continuity equation, then what does it say? It gives us this statement. So, there is no change in density of the fluid, and therefore, the time derivative will go to 0. Also, the density will be invariant. Therefore, it comes out of the dot product. The equation basically becomes like this, which means its divergence V equal to 0. So, we have first looked at the condition of incompressibility through this condition of divergence V equal to 0, which can be shown by two different means. Now, once you have that, additionally, if the flow is irrotational, then we know that the velocity can be expressed as gradient of a scalar, let us say phi. So, when you combine it with the divergence V equal to 0 equation, what do you get? You get a condition like this, and that basically gives you del square phi equal to 0, which is also called Laplacian of phi. So, this is the Laplacian operator essentially. And in Cartesian space, how does it look like? It looks like this. it comprises of second derivatives in space, and it basically operates on phi, and when we set it equal to 0, what we have is Laplace equation. This is basically a second order linear partial differential equation. The word linear has a very deep significance over here. We will explain soon. Whenever you have an irrotational flow field, a velocity potential exists, and therefore, you have a potential flow. Now, here we are dealing with incompressible potential flows, but you can also look at compressible potential flows. We will later see there is a so called full potential equation, which deals with potential flows under compressible situations. Any solution of Laplace equation is called as a harmonic function, and if distinct solutions of Laplace equation are chosen, let us say n number of them, and they are combined. How are they combined? They are combined linearly. So, you have values of the velocity potential coming from different solutions, and you are using different weightage factors to multiply them with and then summing them up. So, you will get a new phi, and this new phi will also be able to satisfy Laplace equation. You can look at it at your spare time as a homework, that how this is possible. You just have to substitute this form into the Laplace equation and see whether it is satisfied or not. So, this is a kind of a superposition property, which is very important, because when we look at incompressible flow fields in irrotational sense, then we can superpose some of these so called elementary flows and ultimately deal with more complex flow fields. We will see in due course how this basically works out. We will look at a quick example. We will see whether a uniform flow that we have discussed in many contexts, we have just assumed a uniform flow, but we would like to check whether a uniform flow does satisfy Laplace equation or not. So, uniform flow first of all satisfies the divergence free condition and also the irrotationality condition. You can also look at it as homework to show how uniform flow actually satisfies these two relations. Remember that here you have to look at del u del x plus del v del y, whether that goes to 0 or not. And here, because you are talking about a planar flow field, that means this is in x y plane, you have to see whether the only component of vorticity which will exist in that case, whether that goes to 0 or not in uniform flow. So, you have to check basically whether these gradients exist for uniform flow or not. Now, having said that, in uniform flow what is happening is that the u component of velocity, that is u infinity, that is what the uniform flow is all about, because it is moving along the x direction. And remember that in terms of the velocity potential, it is equal to del phi del x. There is no v component of velocity, but in terms of the velocity potential it is del phi del y. So, if you integrate this equation, what do you get? You get a relation like this, phi is equal to u infinity x plus some function of y. If you integrate this, what do you get? You get phi equal to 0 plus some function of x. Now, they both should give us a consistent description of the phi for uniform flow. Now, if we compare the two, then obviously the g x should be equal to u infinity x and the f y should be the constant part. Okay. So, finally, you get a description like this, phi is equal to u infinity x plus f y. Now, remember that whenever we want to extract the velocity field details from phi, we have to take gradient of phi, because only from gradient we can extract u's and v's. That means, the moment you take the derivative, then this constant will basically vanish. And remember that f y is essentially a constant. So, the moment you take the derivative, that constant will go away. So, finally, without losing any kind of generality, you can say that the phi for the uniform flow field is equal to u infinity x. That means, this is a possible elementary flow. In a similar manner, you can derive other elementary flows and superpose them and model complex irrotational incompressible flow fields with the approach that we discussed. Since we are running out of time, we will postpone the discussion on boundary layer to the next lecture. So, in this lecture, we looked at some more applications of Bernoulli's equation, and subsequently we discussed about Laplace equation, which is the governing equation for velocity field in an inviscid irrotational incompressible flow. We would discuss the boundary layer flows in the later lecture. Thank you.